Thank you, Professor Thompson, for the introduction. I'm privileged to speak today and elaborate more on the talk by Professor Norford on the urban climate analysis, and also explain what is our effort at CENSAM to achieve a comprehensive analysis. And what we mean by a comprehensive analysis is to have an evaluation that can cover a wide range of physical processes contributing to the urban climate, as well as maintaining the scientific accuracy, but doing that also in the efficient and not too complex manner that can potentially be used by designers and decision makers. So for the purpose of today, and also some of our work mentioned here, we're going to talk about the numerical modeling approach. And I just want to add that even though we are only talking about the numerical tools, they are vigorously validated with the experimental measurements that we have. And we also hope that they work in parallel with the measurements of the urban climate to further inform the modeling as we develop them. So a more narrowed down mission of what we're hoping to accomplish. As the title of the talk also mentioned, our goal is to understand the micro-scale urban climate in more depth and then learn how we can use this information to then inform the mesoscale modeling. So microscale, which is the scale that you and I would interact with the climate and also get affected by climate in terms of emission, heat, and so on, is in the order of the meter, but is very much affected by the urban climate in the neighborhood scale, as well as the mesoscale. And the urban characteristic at these levels, they all affect the holistic urban climate that we experience. And they go both directions. What happens in the urban street canyon microscale affects the larger scale and vice versa. So for the purpose of today's talk, my talk would be on two parts. First, I would talk about one of our projects on microscale modeling, and that's focused on thermal comfort. And the second part would be on an example of how we use microclimate analysis for informing mesoscale modeling, and that's done by urban canopy parameterization. Okay, so first part, thermal comfort. And that's something that probably it's somewhat tangible for us living in Singapore, or even for a short visit. Is this room too cold for you? For me, it is. And it's one of the concerns that not just on daily basis of outdoor environment or being indoor with the AC, but also it's on the news and headlines warning people that there are hotter days to come. And the caption of this figure actually reads that the temperature can be unbearable at times. Wearing lightweight fabrics is a smart choice. And this is due to the strong or the important impact of thermal comfort on health. And even though this concern is very tangible to us, but actually quantifying thermal comfort is rather complex because it depends on various parameters. Not only the air temperature, but also how much you're exposed to the sun, the wind speed, humidity, and as well as your metabolic rate. And even other subjective preferences of thermal comfort, as I mentioned, that some may agree that some range of temperature is comfortable for them and the others disagree. And there are metrics that we can summarize these parameters into one number, mostly normally defined by temperature. And our work so far has been using standard effective temperature. And I'm showing an example here. There is a range of temperature that you can quantify. Okay, if the SCT value is within, let's say, 21 to 26.7, then you're in a comfortable range, and then your feels like would be hotter or colder as you move in different directions. And then this metric would be dynamically changing by factors like wind velocity or how much radiation is you're exposed to, which is indicated by mean radiant temperature. And mean radiant temperature is actually one of the most critical factors to be modeled. And now I'm introducing the model that we have developed in CENSAM OTC 3D, Outdoor Thermal Comfort in 3D. And a big part of this model is about numerical modeling of mean radiant temperature. And that is the reason that it's a very complex factor is that it depends on many geometrical parameters and also surface material properties. Here I'm categorizing it on three main factors. Surface visibility would be one of the first factors. If you're walking in orchard and exposed to surfaces highly reflected, that would be a different story than walking in an open area. And as you move along a street, your visibility of different surfaces would be very different, and also those surfaces may be having different reflective properties, different temperature, and so on. Second factor is the sky view factor, how much of the sky at any pedestrian level that you're located you would see, and what does that mean in terms of the radiation exchange in terms of both long wave and short wave. And lastly, the shadows. Are you in the sunlit or are you in the shaded areas? And in the model that we have, we are able to calculate the mean radiant temperature in high resolution by looking at these three factors. So here I'm showing the schematic of how at every pedestrian point, they're using the schema based on the Tiangang Yi, also postdoc at Sensam, we were able to calculate both visibility of different surfaces as well as the sky view factor. And similarly, calculate in high resolution what would be the sunlit and shaded areas. So one aspect of the thermal comfort model that we have is, and what we think of it as an advantage, is the modular approach that it takes. That instead of developing a model that does all the aspects of urban climate analysis, we rely on the modular approach, which means that this model can implement a work done in energy balance modeling, urban 3D model, and urban flow that has been developed for decades in the field, and use them in very different scales and different resolutions. So for example, for the urban models, we can use it with the parameterized way of urban density, or we have implemented the Python library that Professor Norford mentioned before by Dr. Chen to get the more detailed 3D model of urban area. Similarly, for energy balance, from the very resistant-based nodal points to very detailed temperature distribution of the urban surface can be inputted, and as well as the CFD simulation that will give you the detailed urban flow. And this is also something that we're putting more effort on to make these processes more automated. So we have different models that are developed by different community or within our group, and they each have their own strength and limitation, but when they can be combined together, they would give us the comprehensive analysis that we are hoping to achieve. So for example, one of our effort right now is that we would like to have detailed evaluation of outdoor thermal comfort, as I mentioned, and let's say we have this location in the NUS U-Town, and we want to see what is the distribution of thermal comfort here. Let's say if you want to put a student activity there for a few hours of the day. So we have this thermal comfort model, and it requires certain input. And we've linked that with the energy balance model that will give us the surface temperature. And this is an in-house model, temperature of urban facade, indoor-outdoor building energy balance. But then this model itself has certain limitation that comes from the radiation balance, and it can only deal with more idealized configuration, which is not suitable with the site that I'm mentioning here. So we're now working on co-simulation of this model with a much more elaborate radiative exchange model, DART, by that also one of the collaborators, Dr. Tiangang Yi, is in our group. So we are trying to facilitate this cross-model communication between them so that depending on the case study or the parameters of interest, we can use them together. And this is one example of how we have used the OTC3, the thermal comfort model for a neighborhood in Singapore, using the workflow of getting the 3D model by Chen et al. We got the 3D model of a neighborhood in Singapore, Sengkang, and then also used the energy balance model that was developed in the ETH group at CREATE to get the surface temperature, and and then found the distribution of thermal comfort at different hours of the day. Similar to some of the previous effort that Professor Norford showed, this model is meant to be open source, and we have already included it in the GitHub platform. So it's still an ongoing process, but as you can see here, there are some documentation and examples that will lead you through how to make some idealized geometries or more elaborate 3D model to use or to calculate thermal comfort. So like any other numerical model, what we have developed first is ongoing, and second is always have some advantages and some limitations. The advantages I tried to cover throughout the talk. The modular approach would allow it to be used with a wide range of tools, and it also has a more accurate representation of radiant exposure with high resolution, and also the flexibility in the resolution of the inputs and the geometry implementation. The one main limitation that we are currently investigating is on the representation of vegetation and water body, and also to be able to dynamically calculate the humidity at different points or the pedestrian locations. Additionally, this model only takes into account the microclimate parameters that comes into thermal comfort. As I mentioned, there are a wide range of factors coming from the psychological perception of thermal comfort, and currently these are not integrated. And we looked at the automation with other energy balance model, but we still haven't assessed how it can be automated with CFD, mostly because of the computation cost of the airflow assessment. So last point I want to mention about this is on getting, or our current work, future work of getting more meaningful results from what we are calculating with the OTC 3D. And that comes into context of outdoor thermal comfort autonomy. So how, instead of just having one map for a distribution of thermal comforts in a location at a certain time, we want to be able to know how this space is performing throughout the year. So how autonomous is this outdoor space to keep itself in the desired thermal comfort range without the need to add additional shading, additional cooling equipment. And that's a metric that you can define based on the percentage of the occupied time that are within certain range. And we're currently trying to work to also optimize the calculations that are done in the thermal comfort analysis to be able to get this output instead of just having the one, or having a spatial distribution that would also have the temporal representation as well. And with that, this is the last slide to talk about the thermal comfort. I would like to talk about now our other efforts where we try to use the information we have or the knowledge that we have on the microscale to inform the mesoscale modeling. The work that we have done is with the computational fluid dynamic simulation of microscale. And I have here an example of, let's say we want to do a mesoscale modeling over Singapore, then you would have presumably a domain this size that would also be nested with larger scales. But in this domain that covers Singapore, you would use a grid size that are often in the order of, let's say, from 300 meter to 1 kilometer square. And that means that when you are looking at these grids, even though you can distinguish which of them are over land, urban, or not, but what happens is that the two grid next to each other, one might be covering a place like downtown core in Singapore, and another one Geylang neighborhood. And these have very different urban characteristics, and they also have very different climate, as also mentioned by the even UHI variation of different neighborhood in Singapore. So it is important that even though we're not able to go down to this scale of street canyon and resolve what's happening there, but have enough knowledge to parameterize these characteristics in a different way so that we can represent them in the larger scale urban climate analysis. And this is another representation of let's say, the mesoscale grid that you have. It's big enough to cover a range of microscale and neighborhood scale phenomena that contribute to air quality, thermal comfort, energy consumption, and so on. And the way that we do this parameterization, and what would be the focus of the talk going on, is on using urban canopy parameterization and a multi-layer column model approach. What it means is that it gives information on the parameterization at different heights and different layers, and parameterize for certain effects of buildings in tree, like what is the drag, what would be the turbulent kinetic energy, and the budgets. And to just put that in the context of where does this multi-layer urban canopy model comes in compared to, let's say, CFD or other bulk approach, on the left we have a representation of what the CFD would give you, which is a 3D distribution of the urban flow. And on the right, we have the bulk approach, where you would only represent the urban canopy and what is happening on there with only one node. And the urban canopy model is in between, where it can represent more processes and still is more computationally efficient than what the CFD would achieve. So you have horizontally averaged parameterization at different heights. And this is a work that has been developed for the last 15 years or so, and it started by Martilli et al. 2002, and the use of CFD models, it dates back to 2010, and ever since the drag coefficient, tree foliage, and the radiation and energy balance have been parameterized. The model does well in comparison with the measurements, but there are cases like this when I'll just mention that this is what's now known as BEP3 with this consideration of the both trees and the radiation. But when it was compared with measurements, and this is one of the examples that are showed over Vancouver, you can see that the model has higher temperature estimated than what the measurement is. And now we're looking into what are the factors that are contributing to this overestimation of temperature, and how do we solve that? So we found that the overestimate of temperature is because of underestimation of vertical exchange, and our solutions are as follows. First thing is that, as I mentioned, CFD models are used for the parameterization, and this is the CFD model previously used, RANS. And compared to the other more sophisticated turbulence models like LES, it doesn't represent the full flow characteristic. So our first solution is to use a more sophisticated turbulence modeling of urban flow for parameterization. The second, in simple words, we want to add more physics to the parameterization scheme or the formulation that we have used. There were certain processes previously in the parameterization that were assumed to be negligible and not considered, and now we are with the measurements, we understood that they're actually not negligible, specifically with high-density urban areas, so we're adding those parameterization as well. And the third factor would be to integrate the effect of details of surface heating. In reality, we have surfaces, some shaded and some sunlit, and we are trying to integrate what would be the overall effect of this, as opposed to considering uniform surfaces. And lastly, is to integrate the effect of surface inhomogeneity. So we don't have always idealized arrays of building. We have height variability. We have also spacing difference. So these are the factors that we want to focus on. And so far, the first two have been implemented, and also the last, some of our other colleagues have focused on. And we are currently in the process of evaluating the last two factors. But I will show you some of the results of what we obtained. So this is the LES simulation done over a realistic neighborhood in Vancouver. And this simulation, it covers the area that is surrounding a flux tower in the Vancouver Sunset area. And the goal eventually for these mesoscale models is to represent or be able to get closer to the realistic urban neighborhoods. And now we see that with the improvements that we have with the LES-based urban canopy parameterization, which is the dashed blue line here, we are getting much closer than what the model was before in some of the important characteristics of the urban canopy. And we are doing further analysis to integrate the other factors I mentioned to modify the parameterization. So with that, I would like to conclude. So our goal, as I mentioned in the beginning, is to achieve a comprehensive urban climate analysis. And so far, we've been working on different aspects of either model development or using the current model or improving them for achieving that. And here, I also have a very short overview of what are the other projects that we have today. They are categorized in four main topics of urban ventilation, urban energy, thermal comfort, and urban canopy parameterization. And for today's purpose, we mostly focus on that. With that, I would like to thank you and open for questions.
One question. While Dr. Velasco gets set up, we can take one question for Dr. Nazarian. Yes, over there in the edge.
Hi, thanks for your presentation. So it's very interesting, like your model concept about the short wavelength radiation and with the different shading design, the shading impacts. So I'm wondering whether your numeric modeling concept about the building material, like the long wavelength radiation, that's, so how much do you think how much temperature will change? That's because the long wave radiation emitted from the building surface or vegetation?
If I understand your question correctly, you're wondering how we are integrating the effect of material properties and specifically on the differentiate between long wave and short wave radiation.
Yes.
Okay, so the part where I mentioned the surface visibility and how that comes into effect, that part is actually very important that we also integrate the effect of surface properties. If you are close to a building that is highly reflectant or has a high temperature, both in long wave and short wave, that would affect the mean radiant temperature or the radiation exposure of the pedestrian. So in the modeling aspects, we try to make it in a way that the model can take in those input for material properties and also do that in a separate way for both long wave and short wave. And this will allow also doing sets of either sensitivity analysis or evaluation that can be done to look at the effect of design, look at the effect of these materials on the flow. And I would just add that it is very significant. And just to add to that, there is also a recent measurement study done at Arizona State University that we currently using to validate some parts of the model, and that has specifically shown that the horizontal radiation, both long wave and short wave, has as much effect as the radiation coming from the sky or the sunlit area. So these factors are integrated in the current model.